Thank you. So here is what you can expect from me. I put AI in the context of the digital revolution. I talk about the strengths and fundamental limitations of AI, and I will discuss an idea, a specific idea, how to overcome its limitations. As you know, the world is growing a nervous system in terms of communication, sensing, computing, data handling, storage, and process automation. Mr. Kuppinger has just talked about that. This is what we call the digital revolution. And this is the environment which turned out to be a perfect for AI, which created a perfect storm for AI in terms of hardware support in the form of graphic processing units, which are really were originally addressed to the market of computer games, which had become a possibility on the back of these breathtaking developments in computer graphics. And then, of course, the World Wide Web provides masses of web-based data, which turned out to be the necessary ingredient in artificial intelligence. And that made it possible to scale this idea, which had been published in 1960 by Frank Rosenblatt, the Perceptron, which is a simple network that leads up to decision units. For instance, as to presence or absence of a particular pattern, a dog or so, in the input, made it possible to scale this up to what appeared in a paper in 2012 by these three authors, including Jeff Hinton, which is a perceptron with 650,000 neurons, 60 million parameters, which are the connections between neurons in here. And what was exciting about it was that it reduced the error rate in deciding upon the presence and classifying objects in images. Now, this system has 1,000 output units, so it could decide on 1,000 different categories. This is the error, which was much lower than what was there before. This created a feeding frenzy, which is best illustrated by this graph here, in which the processing power on the vertical axis that is invested in various cutting-edge systems, starting with AlexNet here, and here AlphaGo 0, DeepMind's version of playing the game Go. This is a breathtaking development because the processing power that went into that system had to be increased by a factor of 300,000 to reach that point here over a few years. This amounts to a doubling of computing input into cutting-edge systems, doubling in 3.4 months, much faster than Moore's law, of course. Here is one more data point. The newest conversation piece is GPT-3. As I'm sure you know, this is a system developed by OpenAI, a company owned by Microsoft, originally started by Elon Musk. This system is able to take a sentence, a question, and then continue writing text, which sounds very reasonable in very good English, and stays on the topic. It's an impressive thing. But look at this line here, the newest system. It took in 300 billion tokens, which is essentially words. A word can be one or two or three tokens. 300 billion. If you read at the speed of 10 words per second for continuously 24/7, you would have to read 1,000 years to take in this amount of text. The system has 175 billion parameters, and a petaflop machine, that is a high-performance computer that can produce 10 to the 15 floating point operations per second, would have had to run 3,640 days in order to compute this, the learning task. This is the end of the rope of this field. I don't think it makes sense to go beyond these numbers here. Now, the field is subserved now by downloadable software bases. Young people are very familiar with these terms here. They refer to packages of Python code produced by various organizations here. Young people take a few weeks' time to get trained in this, and they are sucked into this like in a maelstrom. Now, what do we get from AI as this type of AI, deep learning type of AI as a tool? I think the greatest significance of it was to break down the wall that there had always been between the usual world, which is now called the analog world, and the digital world, by systems being able to recognize objects or digits or anything that is shown in a camera. The systems are able to convert speech to text, something you use every day on your smartphone. A largely untapped great potential is data analytics, especially in medical diagnostics, but also in industry, in Industry 4.0 diagnostic of machines for preventive diagnostics. This is going to develop over the next decade, certainly. And then there is natural language processing, you know, translation between different languages, very impressive. But I must say I have little mixed feelings about it, because although the language that is produced sounds very reasonable, it is clear that the system doesn't understand what it is talking about. Let me say a word about the current research environment. It is totally dominated by benchmarks, you know, narrowly defined goals in which, in order to be a player, you have to beat your competition in terms of numbers, like, for instance, recognition rates. The system is totally, the field is totally concentrated on input pattern statistics as the only means of structuring your system. Your system is essentially structured, apart from the initial setup, by the statistics of input patterns, and of course brute force learning. You must have seen 10,000 dogs in order to recognize one of them. The world has to be, the phenomenon to be analyzed has to be shown in all detail during learning time. Now, that has led this fixation, conceptual fixation, has turned the field into a ride in a tunnel. This tunnel is defined by the highly honed software and hardware environment, hardware, the GPUs, you remember, and by education programs. Young people are just sucked into this field. And yet, I think one can say the field is over the peak of its hype. You know, Gartner, with their famous hype cycle, put deep learning here. You know, if you read business reports, it is becoming clear that the cost of collecting and curating data is a burden, and so there is a little sobering in the field. Interestingly, Gartner puts autonomous driving here and predicts it will take another 10 years. You may have noticed that Mercedes has just given up on being a player in this race for totally autonomous level 5 autonomous cars. This is probably not feasible on the basis of the present day technology. So let's think back at what intelligence is about. I find it very convincing. I find very convincing this definition here: achieving general goals in varying contexts. And how does present technology measure up to this? You know, both the digital world and AI in particular are characterized by being, all the systems being of narrow scope, you know, a narrow goal pursued by the system, and they work in rather narrow contexts. If the input leaves that context, systems break down. That is, I think, the main limitation of the field. You know, for instance, when it comes to autonomous driving, the autobahn or the road across the country is no problem. That is handled with great security. But as soon as what they call a corner case, an unusual situation, props up, the system is helpless. It cannot cope with it. Now, this is due to some fundamental problems of AI that need to be overcome. It is, of course, necessary for a full-blown system to integrate subsystems, different sensors, as is the case in our brain, of course, different data sources, memory in our case, motor control, action control, and a goal hierarchy that resides in the system and is not, doesn't need to be imposed application by application from the outside. The systems need to get better at generalization, learning from few examples. The systems need situation awareness in order to cope with varying contexts. And something that is not even spoken about is the systems will need representation of the current situation, something your brain does, of course, in every second of your life. And in order to achieve all of this, systems need to be scaled. Think in terms of numbers of synapses. GPT-3, I've just discussed, has 10 to the 11 synapses. The brain has 10 to the 14. OpenAI has just scaled up this system by a factor of 1,000. It was 10 to the 8 before, but they cannot repeat this feat. This jump is simply not feasible, more for conceptual reasons than for economic reasons. So where can we go from here? Let me just cite one of the gurus of the present field, Geoffrey Hinton, with whom I have already discussed when he did his PhD in Edinburgh a long time ago. He says about deep learning, you know, the thing based on backpropagation of error, my view is throw it all away and start again. How can we start again? I think in order to find the path forward, we have to take the brain for guidance. You may think, oh, God, this is a showstopper. The brain is totally unattainable. This is not my perspective on it. I will discuss just one point about it, which I think is key and can open the door to future development. Let me talk about the information content of the brain. In order to describe the brain's wiring, it takes 10 to the 15 bytes, a petabyte of information. Now, how does this enter the brain? Your genetic information, on the basis of which your whole organism, including the brain, has been created out of a fertilized egg, is 1 gigabyte, 3.3 billion nucleotides. That's all that goes into the construction of your whole organism. You may say, well, the bulk of the information enters the brain through the senses. Not so. We raise our kids in very stable and confined and simple environments, which could easily be reproduced in the style of computer games with virtual reality, which would cost a few gigabytes of program code. And yet kids are able, at the age of 3 or so, to represent their immediate surrounding, act in it purposefully, are conscious of the surrounding, and learn from single examples. They can generalize. So what about this bottleneck? Gigabytes go as input into the brain, and in order to describe its wiring, it takes a petabyte. So where do 99.999% of the information come from? You may think this is a great mystery, but in reality, this question has been studied by research 40 years ago on a particular example, namely the way the fibers growing from the eye in the growing embryo to the brain, this particular brain structure called the optic tectum, how do these fibers find their proper location? Originally, in early stages, it's a complete jumble. The connections are totally dispersed, but after only a few hours or a day, you get a perfect image here when you shine an image into the brain, so that neighboring points here connect to neighboring points there. There was an intensive field of research. Hundreds of experiments were performed to test various theories. I'm proud to be the author of the winning theory together with my friend David Wilshaw, also from Edinburgh. And it is now a system that can be crisply described by mathematics and is well understood. The general theme is that a network of, original network of neurons talks to itself by way of its signals. The signals modify the connections with something called synaptic plasticity, modifying the network until an attractor stage is reached. So the brain is totally dominated by network patterns that are attractors to this process. The process is called network self-organization. So the brain is an overlay of lots of such highly structured network patterns. Let me just talk about one application to face recognition. We know that the face comes into the brain in the form of a two-dimensional field of texture elements, neurons that respond to local textures. We know that these neurons are laterally connected, so they form a network. According to this idea, which I have deployed in two companies, one in Bochum in Germany, the other in Los Angeles, successfully. The idea in this was that in order to recognize that face, you need a model, which is another network with the same structure as this one here, which is static, doesn't move, and is in a particular part of cortex called the fusiform complex. And there is a mechanism for finding out the similarity of the identity of the structure of these networks. That mechanism has the form of fibers that activate on the fast time scale, form a network which connects corresponding points. One calls this process homeomorphy. So this process is dominated by networks that are fluidly created. You know, this face here moves as quickly as the eye moves or as quickly as the person moves. And as quickly move these networks. The networks are composed of little network fragments that have been created during learning time. So in order to go forward, the field has to transform from thinking in terms of individual neurons that classify individual things to think in terms of active networks that self-organize on the fast time scale and organize whatever goes on in the brain. So let me come to my conclusion. AI is caught in a tunnel. A fresh start is needed. The brain has to lead the way, that is my conviction, and the brain is dominated by self-assembled nets. Thank you.